Curvilinear coordinate systems 10, a tokamak fusion device has a geometry that takes the shape of a donut or torus. Calculations for such a device are sometimes done with the toroidal coordinates shown in the figure, the r, theta, and phi coordinates. And we have a major axis and a minor axis, which tells us the angular position on the minor axis. We have phi coordinates. The major axis of the device is a vertical straight line that forms the toroidal axis of symmetry. The minor axis is a circle of fixed radius R0 that passes through the center of the donut. The position of a point is described by the coordinates r, theta, and phi. The coordinates r and theta are similar to a two-dimensional polar system aligned perpendicular to the minor axis. The coordinate phi measures the angular position along the minor axis. So we're going to do the last part of this problem. Laplace's equation written in vector notation is Laplacian phi is equal to 0. What is Laplace's equation expressed in these toroidal coordinates? Okay. Now to answer this question, we have to recall what Laplacian is. Laplacian del square applied to a scalar function phi is the divergence of the gradient of phi. Okay. Now we already know what the gradient is and we already know what the divergence is, so let's apply this knowledge from the previous part. We're going to take the divergence of the following. Now, how do I calculate the gradient from part E? It is ER hat del R. Therefore, I'm going to have del phi. I take a derivative with respect to the R coordinate in ER hat. Plus, then I have 1 over r e theta hat del theta, so it's going to be 1 over r del phi del theta in e theta hat direction, and then I have 1 over r cosine theta e phi hat del phi. So this is 1 over r cosine theta partial derivative with respect to phi in e phi hat direction. This is the gradient of phi. Now we're going to take the divergence of this. For that we need to know the r component, theta component, and phi component. And the divergence was 1 over r, partial derivative with respect to r of r squared multiplied by the r component. So we will have 1 over r squared let's check it, r squared times ar's r derivative. So del r squared. What is the r component of this vector? Del phi del r. this is the operation we have to perform. Next term, 1 over r cosine theta del theta cosine theta times a theta. So we have a theta is equal to 1 over r del phi del theta. We already had 1 over r cosine theta, so this becomes 1 over r square cosine theta. And then we have to take a derivative with respect to theta. With respect to theta of cosine theta times a phi. Cosine theta times a theta. What is a theta here? This is del phi del theta times 1 over r. 1 over r we have already used. So it is cosine theta times del phi del theta. All right. And then we have the last term in the divergence, which is 1 over r cosine theta del phi a phi. A phi is 1 over r cosine theta del phi. So we have the square of that. So plus 1 over r square cosine square theta. And then we take a derivative with respect to phi del phi of del phi, which means we're taking the second derivative. Okay, so that's what we obtain. Now, if I apply the r derivative here, I'm going to get 1 over r square. This derivative will give me 2r del phi del r. Then in the product I leave this alone, therefore the r squares will cancel. I will have second derivative of phi with respect to r. In the second term here, theta derivative gives me minus sine theta. Therefore, I will have 1 over r square cosine theta minus sine theta del phi del theta. And then I'm going to leave cosine theta alone, which means these guys will cancel. I will be left with 1 over r square, 1 over r square del square phi del theta square. And then I have this last term here. I can just copy it. This is our last term. Okay. Now you can see that we have the one of the r's here canceling for this first term. So I can just do that here. This will become 2 over r. Two over r del phi del r. And there is no simplification on these terms, so therefore this is going to be my final answer for the Laplacian of phi. And this must be equal to 0 is the Laplace equation. Therefore, Laplace equation written in toroidal coordinates is basically the Laplacian of phi written in this form is equal to 0. Okay, so in this part, I had to evaluate Laplacian of the scalar function phi. First, I need its gradient. The gradient is qi hat over hi del del qi. So 1 over hr, which is 1 del phi del r e r hat. 1 over h theta, which is r, 1 over r del phi del theta e theta hat. And then 1 over h phi, 1 over r cosine theta del phi e phi hat. Then I take the divergence. Divergence is found in part E, 1 over r squared del del r of r squared times the r component, which is del phi del r. 1 over r cosine theta del del theta of cosine theta a theta. Now a theta is this, so 1 over r cosine theta multiplied with 1 over r squared cosine theta del del theta, cosine theta times del phi del theta. And the last term, 1 over r cosine theta del del phi. There is also a 1 over r cosine theta here, so 1 over r squared cosine squared theta, second derivative with respect to phi, and this simplifies to this final form.